Alright, ladies and gentlemen, moving on right now. We're on section 6.5, day 1. We're talking about the trigonometric form of a complex number. Yes, as it sounds, we're going to mix trigonometry and imaginary numbers together. So we're going to be plotting and finding the absolute value of a complex number and converting between the standard and trig forms of a complex number. Now, if you're wondering right now, why the heck are we going to do this? Well, some of the things we've done with complex numbers in the past, sometimes those were kind of complicated. But by being able to use trigonometric forms of these things, it makes some of those things that we did in the past a little easier to handle. So that's what we're going to do. Alright, so just basics of complex numbers again. Alright, any number can be written as a plus bi, where I is the square root of -1. Okay, that's old news. And for this section, we're going to use z to represent any old complex number. So basically, anytime you see z, you're thinking of a plus bi. So, you know, a and b are whatever real numbers that they are, and that's going to be represented by the letter z. Okay, this should be old news right here, but the complex plane is simply a coordinate plane like you're used to, but the horizontal axis is the real axis and the vertical is the imaginary. So if you like labels, the horizontal is the real axis, and kind of like the x is the reals and the y is the imaginary. So if I'm plotting -3 plus 2i, it's just like having an ordered pair, -3 comma positive 2. So if I go left 3 and up 2, boom, and for our purposes in this set of problems, that's z1. Okay, changing colors here for 2, z2 is 4. Okay, now notice that's the real part, not the imaginary part, so it is the horizontal move. So 4 on the complex plane would be right there. That's our z2. Okay, and then finally, I've got z3 is -5i. Again, I don't have a real part, so it's like having 0 minus 5i. So I don't go left and right, and then I go down 5. 1, 2, 3, 4, 5. So right about there is where my z3 would be for this case. Okay, so basically don't let the lack of one of these parts mess you up. Just pay attention to whether or not you have an I. If you don't have an I, it's the x. If you do have an I, it's the y. Alright, now the absolute value of one of these complex numbers is just like any absolute value, is just the distance from the origin. Well, in this case though, our origin is sitting in a 2D space instead of on a number line, so it's a little more interesting than the regular absolute value that you're used to. Alright, but z is 4 minus 2i, so again, thinking of plotting this guy, I'd go right 4 and then down 2, and that's where my z, my complex number, is sitting. Okay, of course, the distance from the origin is right here. I can draw that reasonably well. Okay, and then again, basically all I need to do is think of this as a right triangle. It's amazing how much Pythagoras shows up in the world, huh? Alright, so again, this was a 4, this was a -2, although I don't really need the negative, but basically then that absolute value of z is going to be the square root, and just thinking of this is my absolute value here, the hypotenuse, so doing the Pythagorean theorem and square rooting both sides kind of all at once, I end up with 4 squared plus -2 squared. Again, the negative is really irrelevant because as you square both sides here, you get a nice positive anyway. So root 20, and of course root 20 simplifies to 2 root 5. So there's your absolute value. But in general, the absolute value of a plus bi, for those of you that want a formula, instead of just kind of a visual representation of it, is kind of what I just right there, the square root of your a part squared plus your b part squared. I guess I didn't need parentheses on those, but they're not going to hurt things. Okay, now let's get to the point where we're actually mixing the trig with these complex numbers. So, as it says here, suppose we have the z, our complex number. It's an angle of theta to the positive x-axis again, so we plotted it, we went over right a and then up b, and that's where we landed. The absolute value of z, let's just use a value of r. We're going to use that more meaningfully in a few minutes. What are the a and b components of z? So again, I just want to really think of this thing as a right triangle of some sort. So I'll just finish the other dotted parts of this, make a nice right angle symbol. Okay, and well, without having any numbers to work with, I'm kind of stuck doing this sort of generically, but here we go. Well, the a is the horizontal bit, and the b is the vertical bit. Okay, so setting up the trigonometric ratios here. Okay, I've got the a, the r, and the theta right here. Those are arranged in a cosine sort of fashion. So I basically got cosine of theta equals a over r. Okay, now I want to know what a is, that's what I was asking. So doing a little multiplying basically gets me a equals r times cosine of theta. Of course that little dot's optional, but there's basically what my a would be. In a very similar fashion, I can set up sine of theta equals b over r. So that lets me know that b is r times sine of theta. Alright, so there's basically how we start mixing a little bit of trig into this. And now completing the full transformation between this standard form right here and the trig form. The trig form here, again, now replacing the a and the b here with what we just figured out gives us z equals r times cosine theta plus r times sine theta times that I. Okay, although that's a little bit messy, so what I'm going to do is factor out the r, and that leaves me with cosine theta plus sine theta I, or times I, but admittedly that's messy. This I, after the theta, really seems messy, so I'm going to bring it over here in front of the sine, and that gives us our kind of final answer, if you will. Any complex number z can be represented as r, that hypotenuse basically, or the absolute value, times the cosine of whatever that angle theta was, plus I times the sine of that exact same angle. Okay, now our book doesn't do this, but when I was learning this stuff, we used a little abbreviation for this, mostly because this angle is going to be the same both times. And then we had cosine, and then we had always a plus, and then it was always I times the sine, again the same angle. So the abbreviation that worked really well and saved a whole lot of writing was r times cis. I'm trying to make a little hook right there. Cis theta. So again, cis means cosine plus I sine. And again, the theta was the same both times, so basically if you want to save yourself having to write that thing twice, or at least whatever you want to call that, you can just reuse cis instead. I will be totally fine with it, even though the book never uses it. Okay, notice in both cases though that r, remember a second ago what we did, going back to our standard form, r is simply, again, the Pythagorean theorem. A squared plus b squared. Alright, so that's what the r is, and let's run with that. Alrighty, so what we want to be able to do now is write the complex number in trig form. Okay, so basically from standard form to trigonometric form. So our goal is going to be this, or again, with what I just said, z equals r times cis theta. Okay, which again is meaning the same thing, just it's a matter of whether you want to abbreviate it or not. Okay, so here we go. Z equals -5 plus 5i. Okay, now conveniently these numbers are going to work out very nicely right here. Alright, so if I've got -5, let's just kind of estimate 5 is about right there, and if I go positive 5 is about right there, okay, making those guys pretty much equal. There's where my z is. Alright, so then imagining a right triangle through what I've made gives me something like that, and hopefully by putting the -5 and 5 on there, you quickly start to think that, hey, that's a 45-degree angle. Alright, so what we need is the theta, which again, as almost everything we do, we measure it from the positive x-axis. So there's our theta, which of course in this case is going to be the 135 degrees, or depending on whether you're doing this in radians degrees, that would be 3 pi over 4. Alright, and then likewise, remember the r is basically the hypotenuse of the right triangle. Again, it's the Pythagorean theorem, so no shocker right there. Alright, so this r value right here, again, based on a couple of 5s, is going to be a 5 root 2. Okay, so basically by putting this information together in our trigonometric form, we get z equals, again, the r is our radius, if you will. That's why I think if they use an r, because it's kind of the radius of a circle, if you were to draw that. Okay, it works out to be 5 root 2. And then again, whether you want one form or the other, it could be as simple as cis 3 pi over 4, or again I could have said cis 135 degrees. So there's that. If you're somebody who doesn't like abbreviations, of course, what you can do is write it as z equals 5 root 2, parentheses, cosine 3 pi over 4, plus I times sine 3 pi over 4. Okay, I will not care one way or the other, whichever you prefer, but there you go. Now on occasion, you might see a complex number written in this fashion, especially relating to this kind of material. Okay, now don't freak out. Basically all we can do here is distribute if you want. Okay, there are some reasonable reasons for leaving it in this sort of form, but quite honestly I'm just more comfortable myself with distributing this guy out, so 4 minus 4 root 3 I. Okay, just be careful again, make sure the I doesn't look like it's under the root. Okay, so again, taking a look at what we have here. Okay, 4 to the right, and then negative 4 root 3 down. So here's my 4 this way, and then 4 root 3 is definitely going to be bigger. 4 root 3, negative. Okay, pretend that's actually perpendicular right there. And then again, what I want to know is this angle there, and then the basic length of this. Well, hopefully it's not too far out of reach to get an 8 for this. Because again, we basically have a 30, 60, 90 triangle. And then again, once we know that, we can do one of two things. Again, call that angle either 300 degrees, or of course that works out to be in radians, 5 pi over 3. And again, depending on what the directions say, you'd have to go with one or the other. Since I did the last one in radians, I'll stick with degrees for this one, but again, pay attention to what the directions ask for. That's more important than what I'm doing right now. So, here we go. So my R equals, okay, again, I want to start my Z equals, I'm going to start out with R, which is 8, and then again, I like my abbreviation, so I'm going to go cis 300 degrees. And again, for those of you who have phobias to abbreviations, it's Z equals 8, parentheses, cosine 300 degrees, plus I times sine of 300 degrees. Okay, I'm lazy, that's why I like to top it. Okay, now if I can turn it from standard form to trig form, I sure better be able to turn it from trig form back to standard. So here we go. So if I've got this 8 cosine 210 degrees plus I sine 210 degrees, I want to show two different ways of doing this, and I'll leave it up to you to decide which one you like better, and I honestly don't have a preference, so whatever you like better is fine with me. Okay, so a graphical version of this. Okay, well, I've got 210 degrees. Again, this angle measured is always going to be the same. If it's ever different, it's a typo. Okay, so 210 degrees takes me, of course, most of the way over to here, and again, drawing this semi to scale gives me a 30-degree angle underneath the x-axis over here in the third quadrant. Alrighty, so from there, again, remember the 8 is basically your radius of this circle that we have here. So this is 8, and then again, no shock based on what the last problem looked like. Okay, I should be able to quickly take my 30, 60, 90 ratios and get a 4 right there, and then a 4 right 3 here. Okay, again, then just paying attention to what quadrants I'm in, this ends up being a negative 4 root 3 and then a negative 4. Okay, and now really these are just the A and the B values for my A plus BI sort of form. So based on that, my Z is, again, here's the real part going horizontally, negative 4 root 3, and then minus, because this is negative, 4 in the imaginary direction. So if you can draw yourself a decent diagram and put it together this way, you can get this in a graphical manner. However, if you're maybe more of an algebraic minded person, then here's maybe a way you want to go. Although I confess algebraic / trigonometric, but we'll go from here. Okay, well, knowing our unit circle stuff, cosine of 210 degrees and sine of 210 degrees shouldn't be that much of a challenge. So again, here's my unit circle, and again, 210, just like in the last thing I did, puts us right about there. But knowing my unit circle values, okay, I know that this right here, my horizontal move, is a negative root 3 over 2, and I know then that the vertical for this triangle is going to be a negative 1/2. Okay, and again, the vertical is always going to be your sine, and then the horizontal is always your cosine. Okay, so basically, replacing the trig functions in my original problem gives me 8 parentheses. Okay, the cosine of 210 again is the negative root 3 over 2. And then I've got plus I times the sine, which is the negative 1/2. Okay. And from here I'll distribute the 8 and kind of rearrange things. Okay, the 8 and the 2 cancel out to be a 4, so I end up with a negative 4 root 3. And again, remember this is what the Z is. Alright. And then I've got a negative here, so there you go. 8 hits the 1/2, becomes a 4, and again the I is just kind of along for the ride. So there's that. So if that looked better to you, great, stick with it. If you like the graphing thing better, great, please do that instead. Alrighty, so here's your assignment. Again, just make sure you know what you're doing. See you in class.